Okay, so the next speaker is my collaborator, Amrutha P from Chennai Mathematical Institute, and her PhD was from ISER Trivandrum. She's going to talk about locally invariant vectors in representations of symmetric groups.
Thank you, Amri, and also thank you the organizers for this invitation. So this is a joint work with Amri and Vel Murugan from IMSC. So suppose let me be a vector space over a field, over complex field. Then a representation is a group homomorphism from G to GLV, that is given any element in G. It will give us a map from a linear transformation from V to V. Now, by an invariant vector, so suppose V is an element in capital V, then we say that this element V is invariant, is an invariant vector for an element in G if rho G, the map rho G fixes this element V. Now, so here I will be interested especially in the case of the symmetric group, and this representations are always class functions. So what will happen is that this will be constant in the conjugacy classes, and so I will be looking on to, so if I pick any element, the conjugacy class I can also mark by the cycle type of the element. So I will be denoting W mu for any element, any permutation in Sn. I can denote it by the cycle type of the element. So my notation will be W mu in Sn for any partition of mu, and also in the number of irreducible representations is exactly equal to the number of conjugacy classes. So therefore, given any representation in Sn will be parameterized by the partitions of n. So I will be using V lambda or rho lambda to irrespective of the notation to say about the irreducible representations of Sn. So in case of Sn, what we are interested in is like we are looking for rho lambda W mu fixes the vector V. So the question we are interested here is that we are looking for the pairs. So we are looking for a pair of a partition and also a conjugacy class element, which will such that there exists a non-zero vector V that is invariant under rho lambda W. So this is the question that we are interested in. And another interpretation to see this is like, to say that suppose this rho lambda G, this is again a linear transformation. So basically what we are looking is like rho lambda G V is equal to V means the eigenvalue is equal to 1. So what we are, the another way of, or another interpretation of this question is like what we are looking is like the permutation, to say that this permutation W mu admits a non-zero invariant vector in V lambda is same as saying that when I restrict rho lambda from the symmetric group to the cyclic group generated by W mu, the trivial representation should be occurring in that restricted restriction of rho lambda. And by Frobenius the number of times, to say that the number of times a trivial representation occurs or any representation occurs, we use this inner product to say the number of times any irreducible representation occurs in the restriction. And by Frobenius reciprocity, we can say that to say that the number of times the trivial occurs in the restriction from Sn to the cyclic group generated by W mu is same as the number of times rho lambda occurs in the induction of the trivial from the cyclic group to Sn. So basically, I can rewrite the first statement, the above statement as so to say that there exists an invariant vector is same as saying that V lambda, so V lambda occurs in this induced representation, the trivial representation induced from the cyclic subgroup generated by W mu to Sn. So the question now we can also translate in this language as we are looking for the pair rho lambda, an irreducible representation, and a conjugacy class W mu, such that this rho lambda should occur in this induced representation. Okay, this is an induced representation from the cyclic subgroup generated by W mu to Sn, the trivial. And a similar problem was considered by something similar to this was considered by Sheila Sundaram. So what she was interested in was like instead of C mu, she was considering set mu, the centralizer of W mu in Sn. And she has shown that when mu is any partition, not of an integer 4 or 8, the V lambda occurs in this induced representation of the trivial if and only if mu has at least two parts and its parts are all odd and distinct. And when we can see that C mu will be a subgroup of set mu. So obviously this induced representation from set mu to Sn will be a sub-representation of this induced representation from C mu to 1. Sorry, C mu to Sn. So basically what I can say is that if V lambda occurs in this induced representation from centralizer to Sn, it will also occur in this induced representation from the cyclic subgroup generated by mu to Sn. And if there's if mu have a distinct pairwise relatively prime, then set mu and C mu will be equal, and our result was consistent with the above result of Sheila Sundaram. Now I will also I would also like to translate the problem in another language of immersion. This definition was given by Devendra Prasad and Ravi Raghunath. So the definition is like if we have two representation rho and sigma, we say that so rho v and sigma w, we say that v is immersed in w if for every, so we just look onto the eigenvalue of these representations, rho evaluated at G and sigma evaluated at G. This will be the complex numbers or the primitive. If suppose the order of G is n, this eigenvalues will be the nth roots of unity. Then the multiplicity of the number of times the omega occurs as an eigenvalue of rho G should be less than or equal to the number of times omega occurs as an eigenvalue of sigma G. Then we say that rho is immersed in sigma, or V is immersed in W. So in particular, if V is a sub-representation, we can always say that V is immersed in W. And in particular, trivial will be immersed in any representation of the group if and only if there is a non-zero vector such that it fixes. So if and only if there exists a non-zero vector that is fixed by G. So this problem was brought to the attention of Amri by Aravind Iyer after a talk given by Dipendra in one of the conference. So this was one of the motivation for this work. And this is our result, main theorem. So what it says is like so the only pairs of partitions that does not admit the non-zero invariant vectors are this finite cases. If you look till 4, so if I pick any integer such a large n, there are only 4 cases for which there won't be for which it does not admit a non-zero invariant vector, except for all these 4, almost all the cases it will be having a non-zero invariant vector. And in terms of immersion, we can state it as like if I for any positive integer n, I can say that the trivial representation V, which I denote it as Vn, the trivial representation of symmetric group is immersed inside V lambda unless V lambda is any of the partitions mentioned in the theorem. Or similarly, I can say that the sign representation is immersed in V lambda unless the conjugate of lambda is in one of the partitions listed in the above theorem. Now I am also giving one more definition. So suppose it is clear that if lambda, or if I'm looking onto the sign representation, the invariant, there won't be any invariant vector unless the conjugacy class is outside the conjugacy class that lies in the alternating group. So I am giving the definition, I am considering, I am saying W mu to be persistent in this, or persistent if the induced representation contains all the irreducible representation except for the lambda equal to 1 to the power n, the sign representation. Now, when mu is equal to n, that is the largest n cycle, the multiplicity with which each irreducible representation will be occurring in the induced representation has a nice is given by a nice statistic called as the major index, and this is well studied. And so, when I consider the induction of this trivial representation from the subgroup generated by the n cycle to the symmetric group, only except for these three partitions, all the irreducible representations will be occurring in the decomposition. This was conjectured by Sheila Sundaram and later on proved by Swanson. So this will be one of the key ingredient for our proof. And I am also using, so the other part we will be using is the Littlewood-Richardson rule. So for that, I'm considering the Frobenius, so corresponding to any irreducible character, I can, using the Frobenius characteristic, I can get a Schur function. So characteristic of chi lambda, the irreducible character of symmetric group, will be equal to the Schur function. And I denote F mu to be equal to the characteristic of this induced representation. And we say that F mu is greater than or equal to S lambda if and only if this V lambda is occurring in this induced representation. Now, in general, if I have any partition mu, I denote S mu to be the Young subgroup corresponding to this cycles of W mu, and D mu be the subgroup generated by the cycles of W mu. And just recall, F mu is the characteristic of this induction from C mu to Sn. And by the property of induction, I can rewrite F mu to be the characteristic of the induction from C mu to D mu to S mu to Sn, using the associativity of induction. And again, definitely, if I look on to the first part, like C mu to D mu, when I induce, it will definitely contain the trivial representation. So I can write F mu is greater than or equal to the characteristic of induction from S mu to Sn, D mu to S mu of the trivial. And this will be equal to, so I can, by using my earlier notation, I can just write it as like the product of F mu wise. Just recall that Swanson has already proved that if I'm considering an n cycle just with one part, the result was already done. So, and so we also showed that, and now I'm giving a sketch of the proof how it will be coming. I won't be going on to the details, but just a sketch of only for this part. So for every partition, if I pick any partition lambda of some integer p plus of the form p plus q, then if every partition alpha of p that is contained in lambda, I can always find a beta of q such that S alpha S beta is greater than or equal to S lambda. For this, here I will be using the Littlewood-Richardson rule. So we know that there is a small typo. S alpha S beta, the product S alpha S beta is given by this summation. That is the number of times each S lambda appears will be equal to C alpha beta lambda. So what we need to show is that this C alpha beta lambda is non-zero. To show that that was my notation for S alpha S beta greater than or equal to lambda. So the C alpha beta lambda is the number of Littlewood-Richardson tableau of shape lambda minus alpha and weight beta. And just recall that it is the number of semi-standard Young tableau whose row reversing word is a lattice permutation. That is the number of times the one appears should be equal to greater than or equal to the number of times two appears, and so on at each step when we are reading from. So the idea of the proof is like we will be constructing T lambda alpha. So we need to show that there exists such a tableau, Littlewood-Richardson tableau. So we will be, the way how we will be constructing it is like we denote T lambda alpha to be the skew tableau. So suppose, so how we will be filling the columns of, how we will be filling the cells in this skew tableau is that in each column, the first row will be filled with a 1. The second row, in each column, the second row will be filled with a 2, and so on. So for example, if I have lambda equal to 5, 4, 4, 1, and alpha is that shaded region, then I need to find a beta that such that this forms a Littlewood-Richardson tableau, or the reverse row reading word is a lattice permutation. So this is the way we will be filling. So when I look on to the, every time the number of time ones appearing will be definitely greater than the number of time two appearing when we are reading from left to right. And so this is so then we will show that if I take any mu to be any partition with two parts, then mu is persistent. The idea again goes by using the previous lemma and using Swanson's result and looking case by case. I haven't I haven't detailed the proof here, and finally we will show that if I have any partition with k greater than or equal to 2, it is persistent if mu tilde is obtained. If mu tilde is obtained by removing a path mu I such that mu is persistent and n minus mu I is greater than or equal to 4. The details of the proof I have omitted. So basically we will be using Swanson's theorem and also the previous lemma, and we will be working case by case to see this. These are the references. Thank you.